Hi everyone, this is Mike from ModelWorks Engineering. I'm going to give a short tutorial on flexures and how we can model them in Ansys Mechanical. When we talk about precision mechanisms like optical stages, metrology instruments, or high-end actuators, we often think of screws, bearings, or servo-driven systems for adjustment and control. But there is another class of mechanisms that enables some of the most accurate machines in the world, flexures, which are compliant mechanisms that allow motion through controlled elastic deformation rather than sliding or rolling contact. This simple principle removes many limitations of conventional joints. Since no surfaces slide against each other, flexures offer perfectly smooth motion with no stick slip, no wear, and zero backlash. This makes them ideal for applications requiring submicron repeatability. In addition, unlike ball screws or set screws that can suffer from frictional heating or mechanical play, flexures deform predictably with temperature and load, enabling stable and linear behavior over long duration. In addition, in actuator systems, flexures can mechanically constrain motion in unwanted directions, meaning the control algorithm does not have to constantly compensate for mechanical errors. And this simplifies control design while improving overall system stiffness and bandwidth. They are also compact and clean, no lubricants, no dust generation, and fewer parts, which are ideal for vacuum environments, clean rooms, and optical assemblies. Last but not least, in fine-tuning setups, instead of turning a set screw that relies on friction and coarse pitch, flexures provide smooth, reversible, and deterministic displacement. When a small external force is applied, the system returns home naturally when unloaded thanks to material elasticity. The model shown here is a cross-axis flexure, a structure that enables independent orthogonal fine-tuning in two directions. Such designs are used in nanopositioning stages, alignment mechanisms in optical benches, microassembly systems, sensor application rigs, etc. Materials that are used for flexures are typically stainless steel or titanium because of their strength and fatigue resistance. And manufacturing is also often done via wire EDM or laser micromachining to achieve thin, precise, compliant blades. And here I will show step by step how to set up a flexure geometry in Ansys Mechanical, apply boundary conditions and loads for a small displacement analysis, evaluate stress distribution, and discuss design trade-offs between compliance, range of motion, and structural integrity. And the flexure that you see in this photo consists of a frame that is fixed using 4 M4 holes on these 4 corners, 20 thin blades, here 0.5 millimeter thick, that are connected to 5 solid blocks. The metrology object is connected to this central block, while the other 4 are used for performing motion in X and Y directions independently. There are also 4 holes to place set screws for applying forces in X and Y directions. For the sake of mesh simplicity, you may ignore these 4 holes, as I will do. Also, it is better to split the body into separate blades and blocks. This can be done in CAD or in Ansys Design Modeler. I have done it already in CAD and created a step file to import as geometry in Ansys. In Ansys, we created a static structural analysis and import our flexures, which is a step file, to our model. And then we double click on the model to open. Okay, now in Mechanical, we go to Geometry. We see that the flexure is already split into separate parts, which are listed over here. We select them all, and we change the material from structural steel to stainless steel. connection between the blades and these solid blocks are automatically created to be binded contacts or glued. We move to mesh. We create separate mesh settings for each of these. We create different mesh settings for the solid blocks, blades, and this frame. Since the focus of the analysis is on the blades deformations, we could set a coarse mesh for these 5 solid blocks and the frame. So we insert a sizing for the solid block and the frame. We select the element size to be 2 millimeters. For the blade, we need a finer mesh. Therefore, we insert sizing for the blades to be 0.5 millimeter. For the selection, we select one of the blades and then select all similar blades. Apply. One important point to mention here is that since the blade thickness is 0.5 millimeter, this 0.5 millimeter mesh size is not enough in the y direction for the blades. Therefore, we have to have more elements in this direction. So the way we do that is to first hide this body so that we could select this edge, and we create a sizing for this edge, and then we select all edges with the same size. Apply. Since we would like to have, for example, 4 elements in this direction, we could divide 0.5 millimeter by 4, which results in 0.125 millimeter. So we basically have 4 elements in the thickness direction. We also apply a sweep mesh for the blades and the solid blocks. And in the method, we select sweep. Now the model is ready to be meshed. We generate mesh. Okay, now we go to the setting. We apply a boundary condition which is fixed support at these 4 corners. We zoom in, select this, select by. We fix these 4 holes. Press apply. The idea of such a flexure is to have fine and accurate motions in X and Y directions independently via these 4 blocks. Therefore, the metrology object that is attached to the central block is supposed to move the exact amount that either of these 4 blocks move. Therefore, we could apply displacement boundary conditions for example, to this area. We would like to move the central block by 0.5 millimeter in X direction. Therefore, we apply a displacement to this surface at 0.5 millimeter, and suppose we would like to move it in y direction for let's say 0.3 millimeter. Therefore we create another displacement. We scope it to this surface, and in the y direction we would like it to move for 0.3 millimeter. To show the performance of the flexure, we request the displacement of the central block and the x and y directions. We would also like to see the stress distribution over the entire flexure. Select equivalent von Mises stress. And in the end, we would like also to know what forces are required, for example, to apply these displacements. We go to probe and create a force reaction. The force reaction could be measured at either of any displacement boundary condition. So we need two of these, one for this displacement and one for this displacement. Now the model is ready to run. We press solve and wait for it to be solved. Now the results are ready. We go to the displacement. As you see, the central block moves exactly 0.5 millimeter in x direction and almost 0.3 millimeter in y direction. That's actually the purpose and the functionality of such a flexure. If you go to equivalent stress, could create a smooth contour and reduce the scale factor a bit, and you see the stress distribution. The maximum stress that the flexure experiences is about 244 megapascal, which is way below stainless steel yield strength. And it is great news because we could increase the range of motion, and the blades are still experiencing elastic behavior. Since the yield strength of stainless steel is about 700 megapascal, we could increase our applied displacements until maximum stress reaches maximum acceptable value. To get a feeling of the motion of the force that is required to move these blocks, we could go to force reaction, and you see for this block to move for half a millimeter, we need 9.98 Newton in the x direction and no other component in other directions. And this block, it needs almost 6 Newton in the vertical direction. To optimize the range of motion and behavior of the flexure, to change the performance and the range of motion of the flexure, we could change the thickness and length of the blades. We could also change the material. I hope you enjoyed this tutorial. If you like this video, please give it a thumbs up and subscribe to my channel. Thank you very much.